You know how scientists figure out if a new drug actually works, or if a study's big finding is for real? Well, it all boils down to this thing called hypothesis testing. And yeah, it sounds super complicated, but we're going to break it down with a simple and honestly pretty delicious story about biryani. Okay, let's get into it. So, picture this. You're in a huge, buzzing biryani hall. The smell is amazing. Everyone's digging in. But then, a whisper starts spreading from table to table like a bad game of telephone. The chicken is spoiled. And just like that, everything grinds to a halt. The head cook hears the rumor, and boom, it's a crisis. If they throw out this gigantic pot of biryani, they're out a ton of money. But if they serve spoiled food, oh, that's way worse. We're talking sick customers, a ruined reputation, the whole shebang. A decision has to be made, and it can't be a guess. It's got to be based on evidence. And that dilemma, right there, is the absolute heart of hypothesis testing. It's just a structured way of looking at two competing ideas about the world and figuring out which one the evidence points to. Is the rumor true, or is it just talk? So the first step is to frame these two possibilities properly. In statistics, we call them hypotheses. The first one is the null hypothesis, or H0. Think of this as the default setting, the business as usual assumption. In our case, it's that the biryani chicken is fine. The other one is the alternative hypothesis, H1. This is the new claim we're actually testing. Here, it's the chicken is spoiled. So what's a cook to do? They need a system, right? A test to figure out what's really going on in that pot. So they decide it's time to run a little experiment. And the cook's method is actually a pretty straightforward three-step game plan. First, you state your two competing ideas. Biryani's fine or it's spoiled. Second, you go out and collect some evidence. And third, you use a rule you decided on beforehand to make the final call. Okay, so for step 2, collecting evidence, the cook sends a few trusted tasters out into the hall to take a bite. Their feedback, whether it tastes off or it's delicious, that becomes the data. These folks are the frontline data collectors in this whole culinary investigation. Now, to make the final decision, the cook needs a really clear rule, and they need it before the test even starts. They set a cutoff point, saying, look, if more than 5% of my tasters complain, that's just too many to be a fluke. I'm going to have to act. This preset threshold, this line in the sand, is called the significance level, or alpha. This brings us to probably the most famous and maybe the most misunderstood idea in all of statistics, the p-value. The cook looks at how many complaints they got and asks this one single question. The p-value is the answer to that question. It tells you just how surprising your results are if we assume the chicken was perfectly fine to begin with. I mean, think about it. If the chicken was totally fine, you'd expect maybe one person to complain, or maybe none at all. So if you get a lot of complaints, the probability, the p-value, of that happening just by random chance is super low. And if that p-value drops below our 5% line in the sand, the cook has to reject the idea that the chicken is fine and conclude, yep, it's spoiled. But, and this is a big but, no test is ever perfect. No matter what the cook decides, there's always a chance they got it wrong. And in statistics, there are two very specific ways you can mess up. Let's break down those two risks. First, you've got a type 1 error. This is basically a false alarm. The cook thinks the biryani's spoiled, throws it all away, but it was actually fine. The consequence? Wasted food, lost money. Annoying, but not a disaster. Then there's the type 2 error. This is a misdetection. The cook decides the food is fine and serves it, but it was actually spoiled. The consequence there is so much worse. People get sick, the restaurant's reputation is toast. Now, each of these errors has a probability attached to it. The chance of making a type 1 error, that false alarm, is actually that 5% significance level, alpha, that we set from the very beginning. The probability of a type 2 error, missing the spoilage when it's really there, that one's called beta. And this brings us to a final, really important idea, power. The power of a test is simply the probability of not making a type 2 error. In our story, it's the chance that our tasters will correctly sniff out the spoiled chicken when it is truly spoiled. You want a powerful test, one that's really good at finding the truth when there's a problem that needs to be found. So, yeah, it's a fun story about biryani, but why does any of this actually matter to you? Well, because this exact same logic is being used every single day to make some of the most critical decisions in our world.
Seriously, every single time you read about a new medical treatment, a new business strategy, a scientific discovery, It is the result of a hypothesis test. The researchers start with a null hypothesis, like this new drug does nothing, and then they collect data to see if there's enough evidence to throw that idea out. They are constantly weighing the risk of a false alarm against the risk of missing a real breakthrough.
All right, to help make all this stick, here are some really great memory hooks from our source. For the hypotheses, just think H0, the hull is okay. H1, the hull is spoiled. For the errors, type 1 is a false alarm. Type 2 is like missing a thief who was really there. It's all about making these abstract things feel a little more real. So the next time you see a big headline announcing some amazing new study, you can look at it with totally new eyes. You can ask yourself, okay, but what were they assuming was true in the first place? What was their null hypothesis? And how much evidence did it really take to change their minds? That right there is the power of thinking like a statistician.